So I'm here to talk about the BlueTides simulation. It's the simulation where we model the first quasars and the galaxies on the Blue Waters supercomputer. And I'm also going to talk about the new development in the simulation software MP-Gadget, the massively parallel version of a gadget that's backing up this simulation on Blue Waters. So my name is Feng, and I'm a postdoc fellow at Berkeley, and the science team involves many researchers in different universities. So, first let's take a look at an introduction. An introduction on the BlueTides simulation. So this is the website, public website of the simulation, and you can find basic information about it. It's a hydrodynamic simulation run on NCSA Blue Waters, and it started from early universe to not so early, but still early universe, redshift of 8. So that's when the universe is a few hundred million years old. And what's making the simulation unique is it's using a lot of particles, many particles, almost 700 billion particles, and it's a large volume, 400 megapascals over H. And these are making this simulation have a huge dynamic range. So in this picture, I'm showing you the background, the entire volume, and we pick some regions and zoom in, we find dynamical galaxies formed in this volume. And that's the power of simulation enabled by Blue Waters. So, this is the backup slide. All right. Yes. So the stage where first the galaxies and the quasars are playing is what we call the epoch of reionization. If we put this into the context of history of the universe, over the 13 billion years, 13.7 billion years age of the universe, the epoch of reionization is a very short period of time. It's a duration about 400 million years. Started when the universe is 400 million years old, ended when it's about 800 million years old. It's during this time, the universe is undergoing a quick phase transition. It turned from opaque, where light doesn't travel, to transparent. Yes. To transparent. And so in this epoch of the universe, many components of physics are at work. There is dark energy, dark matter, and there is neutrino, radiation, hydrodynamics, and atomic physics, and the stellar. Most importantly, the formation of stars and black holes and their feedback, the baryonic physics. So, and what's making this epoch more interesting is in the next few years, there will be a rapid build-up of observational data because of the new satellites like GWST that's supposed to launch really soon. Well, our current understanding, current observation in this epoch, current direct observation of galaxies in this epoch is really, really, few, or the data is really, really few. So we've seen from observations, we've found a handful of galaxies, and most of them are shown here as the red blobs. They are irregular and clumpy. And it's a huge discovery when we found a single quasar in this epoch. It's at a redshift of 7. So these are the current data we have about galaxies and quasars. And the reason we have so few samples of them is not because there are not so many of them out there. It's because our observational power is really, really small. So the state-of-art Hubble Ultra Deep Field, it's roughly covers a volume of 23 megapascal cube per side, from redshift 8 to redshift 12. In contrast, our understanding of modern-day galaxies, the late galaxies, is really well. And this picture on the right shows you the sample we use to measure dark energy, the low redshift galaxy we use to measure dark energy. And putting the Hubble Ultra Deep Field into context is this pale blue point. And if you look at the volume, we only covered about 1 out of 200,000 of the volume we know about the late-day galaxies. There is a huge space for discovery, and NASA is aware of that. So the new satellites are aimed to study this. We'll have programs to study these early first galaxies and quasars. And the projection is we're going to observe about on the order of millions of such galaxies. It's thousands of times more data and covering a much bigger area of the sky. But that does pose the challenges to theoretical modeling, because that means, well, we need comparable simulations that are sufficiently large and with sufficient resolution to resolve the galaxies. And BlueTides is the only simulation out there to do this. So, well, in this picture, I'm showing you the field of view of the BlueTides simulation. It's about 20 degrees. It's not as big as WFIRST, but it's already we're already able to make some predictions based on this volume. In comparison, our current observation is just this tiny little corner. BlueTides, the model in BlueTides is not, well, it's not something we come up. It is the model that predicts the low redshift galaxy formation relatively well. And even at high redshift, poor resolution, apologies, we show that, well, where we have observational data, BlueTides agreed really well with observations. But because the volume of BlueTides is bigger than observation, we can make predictions on it. So, I'm sorry, I don't know what's happening with a missing figure. All right, it's OK. It's a list of papers, so it's fine, it's lost. So the unique position of BlueTides means with this large volume and high resolution, means we can publish papers on this, well, about high redshift that nobody else can talk about, and talk about things that nobody else can quantitatively make predictions. So we've published 11 papers so far. They are either published or in the pipe being peer-reviewed. And all of this progress is made possible by the supercomputer as big and as accessible as BlueWaters, because we need a lot of memory, a lot of CPUs, and a lot of I/O bandwidth. These two circles were just circling papers published by new graduate students starting their career analyzing the BlueTides data. But yeah, sorry, the name is not there because the figure is missing. So it's completely gone out now. Oh, all right, we're still fine, I guess. So here are a few examples of this of the science we do with BlueTides. The first is in this example, well, we showed that if given our volumes bigger than current observation, we do expect to see a bunch of galaxies with that are very massive, and they carry with a rotationally supported disk structure. That's very different from the current population we have seen from observations. And more interestingly, in March, highlighted progress is the observers found the redshift 11 galaxy. It's the highest redshift galaxy that's been observed so far, and it's after we've done the BlueTides work. So if we put that galaxy, the black point, on the attributes on the property of the population of galaxies we found in simulated in BlueTides, it's right in the context. It's right. The green is the area, and I'm showing here the mass, the stellar mass, stellar formation rate, and the age of the galaxy. It's right on the spot. So we have prediction powers. Another example is BlueTides can make a prediction because of the large volume. It can make a prediction of galaxy clustering measurement from the WFIRST satellite samples. And we showed that if the WFIRST instrument can improve their spectrograph from being able to do redshift 9 all the way down to redshift 8, where they have observations on galaxies, this sample of galaxies can actually make a very precise dark energy measurement of dark energy. And that can even be better than our current smoking gun measurement from the low redshift galaxies. So this shows that, well, our result can actually have feedback on the design of new instruments. So, and the final example here is data from BlueTides simulation reveals how quasars and their hosting galaxies can co-evolve or not co-evolve together. So what we found from the data is that, from the simulation data, is that when the tidal field is strong, the galaxies tend to form in a filament, and when the gas falls into the galaxy, they form a rotationally supported disk where a star forms. If the tidal field is weak, then as the gas fall in, they directly fall into the central massive black hole and feed the growth of the black hole, turning the galaxy into a quasar. So that this sort of like a study requires us to start from a simulation that's with sufficiently large volume to cover these samples of objects. So this sort of science we do with BlueTides, or because we can run a simulation this big with this many particles and fit it into the memory and the computing power of blue waters. Of course, while we are doing science, we're not sitting idle about the software. So we're also making progress on continuing development of the software behind BlueTides, the software MP-Gadget. So this is the software. Basically, it's a hydrodynamics and a gravity solver for cosmological simulations. It implements multiple physics models of baryonic physics. And the striking attribute of this software is it scales from as small as a laptop to blue water's machine full capability. So the idea behind this software is we want to use this software to push the envelope of computing in cosmology and astrophysics on full machine capability scale computing facilities like blue waters. And therefore, continuous access to blue water's resource, including computing resource and the staff support, is crucially important for the development of this code. So in MP-Gadget, MP-Gadget is a branch of Gadget where we have made significant improvements on the particle mesh long-range solver and the I/O. We also made improvements, but we didn't completely rewrite the modules for domain decomposition and the short-range solvers. So, and by looking back at the calendar, we realized this thing. The software Gadget, the family of Gadget simulation software has been around for almost 20 years. And it started relatively simple from version 1.0, where it's about 10,000 lines of code, and when at the year 2011, when we were running massive black simulations at Kraken, the software has blown up to 100,000 lines of code. It's it's 10 times more code doing roughly similar stuff. So, well, this is, of course, we realize there is probably some issues. So one topic we've been working on is to reduce the clutter in the code and make it more sustainable. So our current master branch on GitHub of MP-Gadget, it has 23,000 lines. And we are still working on reducing the complexity of the code to get it ready for the future. And this shows the focus of development. During BlueTides, we were looking at like improving existing capabilities. So the number of lines dropped to 70,000 because we replaced the particle mesh solver and hugely rewrite the threading part of the code. That alone reduced the complexity of code by 40,000 lines. And the current version, we further reduced the lines, and I'll show you what we are doing there. So the basic idea is we get rid of the code. We remove the unused, deprecated, or duplicate code from the code base, identify them, figure out why they are bad, and remove them, replace them with better code. And we are also in the process, we are removing unlicensed code where we can't even trace the author. So that's because the purpose is we want to open source this code. And a huge progress is we eliminate all of the nested if-def blocks. If you do programming, you know these things are nightmares, right? You don't really know, even after a while, you don't even know which branch of the code you're running. So, and the initial condition solver is ported to use the main particle mesh solver. So that eliminates a huge chunk of code. And then the short range, the baryon feedback modules, the black hole, star formation, and the halo finder, they are now ported to use the new threaded tree evaluator code. So that allows us to have only one copy of this tree evaluation code, and that's fully threaded and we can work on. So we also improved the build system. Now we do off-tree compilation by default, and we also simplified the makefile flags, making that list flat without interdependency. So it's harder to break it. And we also added a new parameter file parser. This parser is unique in the sense that it requires the extension modules to declare their parameters with like whether or not this parameter is required, what's the recommended value, and what is the help string. So basically, writing new modules for this code, you have to make it self-documented. And the idea is we make the code linear so we can run faster and longer with this flatter and low redundancy and self-contained coding style. This is the way for the future. So on this improved code base, we are already implementing new modules or merging existing modules into the new code base. So we've implemented the new treatments or additional treatments on radiation and the neutrino components in the Hubble expansion, and we added the quick Lyman alpha forest model where we make approximations such that the code is optimized to simulate intergalactic medium and Lyman alpha forest. And in progress work is we are developing a new model to model the intercluster medium physics. So that's a lower resolution baryon feedback model. And what is really on our plan that's going to be due next, a huge amount of work, is we want to look into this domain decomposition scheme. We want to implement a new domain decomposition scheme that uses less memory, because that will allow us to further over-decompose the domains and reduce the load balance in all of the short-range solvers, including the hydrodynamics. And that's that. So we are also making progress on the I/O performance, understanding what we were doing and why it was good, actually, through the paid program. So the paid program is we are paired with this IME team from University of Illinois, with Darren Adams, William Grob, Lu Huang, and Ed Karens. Lu Huang has just graduated over last year. And well, we also have a student in the science team that's working on this project. A new student, Markus Scheucher. And well, so what we realized is when we look at the logs and measure the BlueTides I/O throughput, we achieved 500 gigabytes per second, and that's quite fast, actually. It was one of the fastest drops in the system. So to understand what we were actually doing, right, because it was just something coded up overnight, right? So to understand what we were doing, we actually implemented Sam is implemented this benchmark tool that can simulate the I/O of BlueTides, and well, can also do general purpose benchmarking of the computing facilities if you look at it from another perspective. So, I'm missing another figure here. I don't know why. So, well, this I/O system of MP-Gadget is called bigfile library. The idea is, we want to have a library to handle big chunks of binary data, and the idea here is we want the data to be hierarchical, but the hierarchy is not containing any single file container, but it's just exposed through the file system. So that reduces the overhead, and we also do the splicing of the binary data directly on the file level to avoid playing with last magics. Then all of the metadata, including the schema of data and attributes of data sets, they are stored in plain text. So you can open it with VI and read what is there. And the library is very available, so you can reuse it either by linking or simply include the header file, include the C code in your code. And that's actually how we make the Python binding. So it's freely available. And when we put this library, when we implement this library in MP-Gadget, comparing to the compressed HDF5 file we used in previous benchmarks, it's at least 10 times faster. And the idea, and also we are using less number of lines. The old I/O was 5,000 lines just to write a file. Now we are doing 800 lines, which is still a lot, but considering what we are doing, it's actually quite an achievement. And yes, so we are doing, this is the result from the initial benchmark runs on Blue Waters. And we've actually been able to identify hotspots in the code with this tool. I think it's Tau. This is from Tau. And basically, these 3 bars here shows you the time in sequential truncation of files when we create a data block on the disk. And also, the second block is when we are calculating the checksums of the data. And the third block is when we are casting the types of data from the internal representation in memory to the type we want to dump on the disk. But these 3 are using quite a lot of time, and that's where we want to investigate further through the paid program to make the library even better and faster. So This is my last slide about software. I want to talk about the reusable components in MP-Gadget. So all of the new components we wrote for MP-Gadget, we insist on having them reusable. So they are provided as libraries. And actually, during the last year, we insist on every of these have a full Python binding. And all of the headers are C++ compatible. So that made sure these components can be used in other projects. And actually, we are doing that. So the fast PM code is a particle mesh solver without hydro or tree. And this code is using the Fourier transform library and the I/O library of MP-Gadget. So, and also the Python, based on the Python bindings of these things, we are building a post-data analysis for embodied simulations. It's called embody-Kate. And the idea is all of the analyses are done in massively parallel way with the Python. So we typically do 500 CPUs MPI ranks with Python for these analyses. And all of these are published or being published. And the idea here is software being tested and developed on Blue Waters with the state-of-art supercomputing facilities. And then they can directly, all of these improvements can directly improve all of the other downstream applications. So that's a sort of like impact from our work on Blue Waters. As a summary, my final slide summary. So we are doing a lot of science and scientific computing on Blue Waters, and on the science side of things, we are making interesting discoveries on first galaxies and quasars from the BlueTides simulation. We're making predictions on WFS and JWST satellites, and we are also investigating the physical mechanisms behind the formation of first quasar galaxies with this simulation. On the software side, the support from Blue Waters allowed us to continue the development of this amazing software, MP-Gadget, making it leaner and more sustainable for future development. And we are implementing new physics models and heading towards a better domain decomposition scheme. And also pairing with the paid program with the University of Illinois team, we are improving the I/O performance and actually understanding and improving the I/O performance of this of the MP-Gadget software. And all of these major components in the software can be reused and are being reused in other research projects in cosmology, and that's well, saving some work, right? So. And I'm entertaining all of us with this picture of BlueTides on Blue Waters and making predictions on telescopes in the space. And that's it.